Welcome to the fourth session of the webinar series. Now Ayush will start the session. Over to you, Ayush.
So good evening, everyone. I'll just share my screen and we'll get started. Hope you can see my screen. So today is the fourth session in the series of sessions related to LLM development that we are doing. And the fourth session, I have requested to just swap the sessions from fifth to fourth, because the last session was a bit theoretical, where we discussed like a lot of parallelism strategies. So I thought let's make it more intuitive this time and try to swap the session so we can cover the RL and the post-training part and the evaluation in the last session, that is the next Wednesday. So today we will be going to see how we are going to deploy the foundation models, what are the challenges and best practices that we should adopt, what are the different criteria in terms of metrics, inference metrics that we have to take care of, and how do we assess or estimate how many number of GPUs we are going to require with certain conditions, like these many users are going to use a service for these many days and so on. So let's get started. This is, as I mentioned, this is fourth in the session. Now the fifth session, we have just swapped it. So this session is fine tuning and deployment, where we'll be covering following things today. First is what is the basics of inference, as in how does the LLMs or to be very specific, transformer architecture actually do forward pass? What are the different stages in which, and how much time does each stage take for a single forward pass? So this is forward pass is basically an inference. Then we'll look into the metrics, which are like those hamper or affect our experience of the user. So these metrics we are going to look at it. Then inference engines, like how can we optimize our model for the underlying hardware by the consequence of using quantization, sparsity, and so on. And then can we do runtime optimization? So there are like offline optimizations, and can we do runtime optimizations like in-flight batching to improve the experience of the user and utilize the hardware to increase the throughput or increase the efficiency of the output? And at the end, we are going to see like how do we calculate for a given model? How do we calculate for how much GPUs would be required for serving a given number of users? So as we know, inference has become more and more challenging because we have a very large model, and recently, due to the availability of reasoning models, the thinking time or the time to output or to present the user has increased multiple fold. So and in addition to that, like DeepSeek kind of models, they produce intermediate tokens a lot more than the previous non-reasoning kind of models. So now the inference has become a bit more challenging because we need to improve the experience of the user as well as do thinking in the background as an intermediate stage for the reasoning kind of models. And with the models like Llama 4, which now has like 10 million context size, so there is like millions of input tokens, and the output tokens could be a lot lesser than the input tokens. So with multi-turn conversations, we ought to have like more and more input tokens, which becomes a context for these LLMs. And with the introduction of agents, which require more compute for improving the tool calling ability or improving the overall workflow of the enterprises, inference compute time requirements are exploding. Now, what is LLM inference? It begins when the model receives an input prompt, which can be in various forms. It could be text, image, audio, and now it could be a sequence of frames or sequence of images as well, because now we have like video models which are producing videos. For a given input video, it can autocomplete or complete the next set of frames to produce the next set of video frames. So input prompt could be any of them. And for text-based models, this prompt is generally tokenized, that is splitted into smaller units called tokens. and this becomes the basic unit for the model to analyze. During inference, the model uses the parameters that it has learned during training. So model uses those parameters to process these tokens and produce outputs. So once the output is produced, the deep tokenization stage happens that converts the output token, the subwords, back into the human readable or complete set of words. And then there are finally multiple use cases for the content generation, summarization, translation, and so on. Now, as I mentioned, tokens are basic units for LLM that allow models to break down and analyze large pieces of information. So these are tiny units of data, and typically they are 4 characters in English. But even beyond text, for images, tokens may correspond to group of pixels or patches or image patches, basically. So these generative AI models learn by predicting the next token in a sequence. So the loss function for these transformer models is the cross entropy loss typically, but the idea intuitively is to predict the next token in the sequence. So it's a next token prediction problem. After training, these tokens that are generated during inference and generate tokens, and these responses are produced. So the efficiency of token processing is quite important, because the quicker the tokens are processed, the faster the model can learn and respond. And tokens directly influence the cost and efficiency of operations. So in various blogs or websites, you might have seen that now the value chain of AI development has been changed from just producing results to or evaluated in the form of token generation. So because this token generation directly influences the underlying GPU hardware that is required to produce these, how much efficiency or how much throughput, in the sense like with how much latency in the gap between tokens and so on. So basically, for the overall experience of the user, these tokens serve as a building blocks, both from the LLM or the transformer architecture, that is the AI architecture perspective, and also from the operations perspective. And now we know, like, many platforms often charge based on token usage, and these have by default becomes a measurable unit for AI applications now. So now, as I mentioned, there are multiple stages within the transformer architecture, and tokenization is one. Then there is an embedding lookup. Then there is a positional encoding. So each stage has a different compute or memory requirement. But most of the time, for a single forward pass, most of the time, like 35% time for the whole complete inference timeline, inference time is taken by the attention blocks and the feed forward blocks, which takes like 45% of the overall inference time. And there are like other stages like KV cache, output projection, sampling, which is like greedy sampling. When you do decoding of the produced tokens, the sampling takes like 2% of the time. So essentially, we are mostly interested in these two blocks or these two layers, attention and MLP, which essentially it takes the most of the parameters as well, and also takes most of the time while doing the inference. I find this particular figure pretty striking because, like, it gives you a quantitative understanding of how much time is taken by each stage during a forward pass. Expectedly, attention and MLP has to be the largest, but yeah, this gives you a like complete idea. Like both these stages takes 80% of the time, and this takes like 20% of the time. So now coming back to the inference measurement. So we'll now look at the metrics that are useful to understand the overall inference workflow of the LLM. So one of the key measurement metric is time to first token. So when a request is sent by the client through the network as a stream, tokenization happens when the characters or sequences are converted to vectors. Then you have all those vectors from a request, and you have to compute the attention metrics between those tokens. As we saw in previous slide, like 35% of the time is taken by the attention layer. So these attention metrics computation or the self-attention layer, you have to find out like how multiply your input by the query key and weight matrices, and then you have to do an operation, several operations like softmax or dot matrix multiplication operation to find out the or to fill the attention matrix. Now this attention matrix serves as a key value. There are separate keys and values metrics, so they are also served as a used to cache, because these are again used when we are going to generate more tokens. When we are going to decode in the next stage, we are going to reuse these keys and values that are generated during this by this attention layer. So overall, this is what we call the stage of prefill. After prefill, only one token is generated. So the full process is measured when you see time to first token. So let's say you have a summarization use case where you have a couple of pages to summarize, which let's say consists of 2000 tokens. So all the 2000 tokens are going to through a tokenization stage, and then there will be a matrix of size, the embedding size and the context, that is 2000. It's going to be computed for keys, values, and for the given input query. And so this is this attention matrix takes a lot of time, and this is the prefill stage that we call, because this is compute heavy, because we are doing a lot of operations here for dot matrix, doing a softmax operation and so on. So that's why this is a compute heavy or compute bound process. So we call this as a prefill stage, and we measure this in terms of how much time does it take to generate a first token. And now, once we generate the first token, the subsequent tokens are generated in autoregressive manner, because the transformer is an autoregressive architecture. Now, after computing all the attention for the input tokens, once first token is generated, we just have to compute the attention with respect to the first token, because we are storing all the keys and values generated for the previous input or the complete input or prompt into a cache. So that helps us to reduce the time taken for generating the complete sequence. But from the measurement perspective, during the generation phase, we have multiple tokens generated one by one by the LLM, and to stream them, they have to be de-tokenized and then sent to the client. So what the inter-token latency is, it's typically the measurement between those tokens received by the client. So this matrix is sometimes called time per output token, and as well in the literature. So essentially, if you assume like the networking transmission time for each token is same, so inter-token latency measurement in the client is same as inter-token latency during the decoding and generation phase, because during the generation phase also for the first token, we are going to transmit it through the network. So this is another metric which is useful to understand how much time is being taken to generate each token on an average by the model. So the total time to generation is the prefill stage, that is the first token, time to first token, and the decode stage. So I forgot to mention this particular inter-token latency or the complete generation phase, we call it as a decode phase. So first was the prefill phase, which was time to first token, and then there is a decode phase. So the sum of the time to first token and the inter-token latency on an average for all the tokens that are generated, when we multiply them by the number of tokens, we get the overall end-to-end latency for our model. So these are like typical throughput metrics the metrics to measure the inference capability of the model. So whenever we are going to assess the throughput or latency of the model, we are going to ask these specific questions, like what is the model, how many parameters does it have, what precision are we doing adopting for the parameters, what is the input and output length on an average, concurrency, like how many users do we expect on an average or at the peak to access the model simultaneously, and what is the tensor parallelism. So if our model does not fit within a single GPU, is it going to be split through by tensor parallelism, tensor parallel technique across multiple GPUs. So we saw these parallel techniques like tensor parallelism, pipeline parallelism, data parallelism in our previous session. So to measure the efficiency, inference efficiency of the model, we adopt things like request per second per instance or request per second per GPU. So this refers to how many requests can a model take in a second when it is deployed in a GPU. Like, let's say if the model fits within a GPU, then okay, we can just have to calculate requests per second. But if model does not fit within a GPU, it's a larger model, then we average that and find out like per GPU what is the maximum number of requests that the model can take. So these particular things are useful when we are going to do a hands-on or see in this session, a demonstration. Like we are going to specify all of these things and then compute like request per second, and then based on our conditions, like what is the maximum latency that we can probably take care of, like we can handle the service latency basically, because we need to specifically mention if we are going to deploy this model at the enterprise level, then what is the average latency, like time to first token or the end-to-end latency that we can probably have. So that defines like how much GPUs or how many requests that how much infrastructure do we need to build for this model inference. So yeah, so this inference latency, as we discussed, there's an input sequence length of tokens that is fed into the model, which generates the output sequence length one at a time. Time to first token, I'll just repeat it for the sake of clarity, measures the time it takes for the model to generate the first token after receiving a request, so which indicates like how long an end user needs to wait before seeing the first token. And this part of execution is called as prefill stage. And this particular time to first token is essential in use cases like customer support or e-commerce bots, like where the user expects the response as soon as possible. And inter-token latency refers to the time interval between consecutive tokens. So because the token generation, the time between two consecutive token generation should be lesser than what a normal human reading speed should be, because we want to generate tokens faster than what a human can read, so that the user do not have to stop before reading and wait for the next token. So the delay, so overall end-to-end latency is time to first token plus the decoding latency. Decoding latency is the overall generation of tokens. And yeah, so latency is like very critical to ensure smooth user experiences. And we want to maximize overall system efficiency while providing good user experience. Yeah, so from the model perspective, it's I think necessary to understand this very important concept that is underlying like all inference now techniques, which is the prefill, distinction of prefill and decoding during token generation. So as I mentioned, prefill is the stage until the first token is generated. So it includes like loading the input tokens, computing the first KV cache, because this is a compute bound process for if you have a reasonable prompt length. Like what does reasonable prompt length means is if your input length is not very small, then this process is going to be compute bound. So there is more computation than the memory calling for this whole prefill stage. So that's why there's a compute bound process. So once the first output token is generated, we go into the decoding phase. using the KV cache, this is much less compute intensive and mostly consists of accessing the KV cache. Hence, it is going to be a memory bound process. And if you look at this animation particularly, the user request goes in. There's a compute bound process which goes in the prefill phase. So these are like KV cache which are computed, and then there is going to be decoding phase, which is going to be a memory bound once first output token is generated, right? So this is how the overall basically two stages of LLM execution happens. And now in a distributed inferencing setups, people are trying to, or they have successfully separated this prefill and decoding stages and then deployed them into different nodes or different GPUs, so that these memory bound and compute bound process can operate simultaneously for different batches. So we are going to see that latest advancement in inference engines like vLLM, Triton, TensorRT, and SGLang are able to do this distributed inferencing for large models. Yeah, so again, this is again a representation of like how does prefill and decoding happens. Let's skip this. Yeah, and come back to this point. Like, so AI training involves like data processing and training the model, and AI inferencing particularly have two stages or like two typical workflows. One is optimizing the model for the underlying hardware, and then deploying the model for optimal user experience and total and TCO, and optimizing the TCO, total cost of ownership. And for these, NVIDIA has like separate SDKs, software libraries that helps you doing all this stuff. So TensorRT helps you to optimize the model for the underlying hardware. So the optimizing the model could mean different things. So we are going to see this in the subsequent slides. Yeah, and now we have seen like two important things. One is what does inferencing means, both in terms of prefill and decoding. And secondly, we looked at the metrics, which is used to measure the inference efficiency of the model. But then we are going to see now, like, how do we evaluate or how do we benchmark our models? Like, let's say if you have developed a model from scratch, or you are reusing some model, how do you benchmark on your hardware, like to estimate how many GPUs or how much infrastructure you should build or assign to your model to ensure that your user experience is smooth. So this is one tool, and again, it's a GitHub library, GenAI-Perf. It's a LLM benchmarking tool. It provides metrics like time to first token, inter-token latency, request per second, and more. And you can use it to measure performance for any inference endpoint. So that inference endpoint should have OpenAI specification, and you should be able to analyze under different scenarios like concurrency, latency, or throughput. You can specify, you can understand how much GPU infrastructure is needed for your use case. So we are going to do a demonstration of this. So this is a typical output of a GenAI command. Here you see that it provides these metrics: time to first token, inter-token latency, request latency, and so on. So instead of going through this, I'll just take you through a demo. And yeah, this is again, it gives you a visualization in terms of like for the given time, let's say for the given concurrency, like these are the concurrency 1, 2, 5, 10, 25, 50, 100, and so on. So for these given concurrency, what is the time to first token? How much is the time to first token, and what is the overall throughput of the system, like in terms of tokens per second, or how many requests per second are going to be served? So this gives you like across multiple scenarios the understanding about the overall benchmarking, inference benchmarking. So now instead of going through this inference engine, I'll just take you through a demonstration to show you how does it work. This GenAI work. Just to give me a second, I'll just share my complete screen now. Yeah. Hope you can see the VS Code screen. So there are two ways to analyze it, analyze your performance benchmark. One is you already have your endpoint with you. So if you already have an endpoint over which you have to do this complete analysis, then you don't need to specify all these NIM container that I downloaded. Otherwise, if you want to evaluate the performance of an existing model, then you just need to specify like the container image. So this is again we'll probably cover in next few sessions. This is a NVIDIA inference microservices. So basically, these are pre-built containers containing this Llama 3.18b instruct model. And once you download the Docker and launch, once you download the Docker and just execute it, it will launch an OpenAI endpoint. So it will just give you an inference endpoint over which you can just make a request and receive a response. So I just defined these models, these Docker containers containing these models, and the benefit of having these Docker containers, these images, is that these are pre-optimized and built by the NVIDIA. So this Llama 3.18b is already, once you download the model, it will choose a profile which is optimized for your underlying hardware. So it will also choose, it will also give you an option to choose like what quantization do you want to, what quantized model do you want to pull from the web or pull from the Docker repository. So this is the benefit of having the NIM container. Apart from this, there, as I mentioned, these are like optimized. There are several optimizations which is already done by the NVIDIA. So you can just download it and get an inference endpoint. Once you get the inference endpoint, this script will help you. I showed you this script. So this script will help you to do this analysis or make a test or evaluate like under what concurrency, under what throughput scenarios, what my performance would be. And finally, it will give you generate this folder. So this on the left side. So under concurrency 1, it will generate like this particular folder for me, like for the scenario where the input sequence length was 200 and output sequence length was 200, I received this latency, right? This average request per second. So you can, it gives you you can evaluate like different use cases. You can also define your own use case. Like I just tested it on 2 different use cases. One is translation, where the input and output sequence length is same, and one which is the summary, where the input is relatively or quite higher sequence length than the output sequence length. So once you get this sweeps of concurrency under different use cases, you will get these different JSON files. And then you can analyze these JSON file using this Python notebook. So I'm going to upload the complete setup on the GitHub repository. And what you get in the complete setup is, I'll take you through that. Yeah. Yeah. So what you get in this complete setup is this particular thing. So you can choose in this notebook, you can analyze like under different scenarios. Let's say my first token, and let's say my I want to see on the y-axis like output tokens per second. Okay. So let's say if I hover here under the concurrency 1, where the input length and output length is 512 and 128 respectively, I'll receive my latency to first token would be around like 1.5 to 2 milliseconds. And the output tokens is going to be around like 200 or 300 per GPU. Because my concurrency is less, my GPU will be idle for most of the case, because I'm receiving like only request only once in a block. So there's no batching because there's only a single block. And as I increase the concurrency here, if I go to the concurrency where the concurrency is 25, I have a latency which is increased. Now it's going to be 200. So the user will see first token after giving the input or the enter to your application. It will receive the first token after 200 milliseconds, except like not discounting all the not taking the network latency into consideration at this point. So you'll receive this much first token latency. So as expected, when you increase the concurrency, your output tokens per second for the GPU, there will be more utilization of that, but you will suffer from the latency point of view. So there is typical trade-off between throughput and latency. So throughput that you will receive from GPU. So you can also change like how much output tokens per second per GPU you can receive. So for the 25 latency, you will receive like around 700 or 750 output tokens per second per GPU. So even though your latency is high, your throughput is also high. So you are able to take the maximum juice out of the GPU. So this is like typical analysis you can do. And in addition to this, there is another interactive notebook that I've created. So this basically to estimate like how many GPUs do you need to serve the users, giving them a smooth experiences under some latency or throughput considerations, right? So there are like two conditions. One is like latency, how much time to first token latency or end-to-end latency that you can accommodate. So and then there is a throughput trade-off. Like if you are going to able to accommodate higher throughput, you have to accommodate like lower latency, right, for the user. So now in this case, like if you have, since I choose only two configs for the input and output sequence length, if I increase my concurrency, like if you see here, if you increase my request per second, so again, the tokens per second and request per second are similar, but we do it more in terms of request per second because that is more intuitive to the readers. That's why I choose request per second, and that is more standardized way to evaluate your inference pipeline or workflow. So now if you see here, if your target request per second, so let's say your throughput that you are expecting from the underlying GPU is like let's say 153 requests that your GPU can serve, then you need, and for the concurrency of 45, because you are, let's say you are expecting higher number of users hitting your servers, then you need like these many GPUs, like 21 GPUs to serve with this time to first token. So with this particular condition, like your time to first token should be 378. You require 21 GPUs to serve like 45 concurrent users. Okay, so this will help you in doing this. So let's say if your concurrency is lesser, so your expected time to first token is going to be 64 milliseconds, and your request per second, if let's say is again 153, or if let's say I'm going to reduce it to 30, so you require like lesser number of GPUs, like only 19 GPUs to serve the users. Okay, so this will give you an idea about, like, for the given scenarios and the under conditions like latency, how many GPUs you should probably need to serve your users. Okay, and then there are like different. Yeah, I'll just take you through one figure. Yeah, this particular figure. So again, this is for the same Llama 3.1 8B model. So again, this is for blue line is for input sequence length 512 and red is for 200. Now for concurrency of 5, you will get like 6.7 requests per second. If you increase concurrency, obviously you are going to have a higher throughput or higher request per second. But when you increase your concurrency, you are going to also have an impact upon the experience of the user in terms of time to first token or TTFT. So again, this will give you an idea like how much you can accommodate, how far you need to allocate the infrastructure for the underlying thing. So this is the overall performance benchmark analysis, and you can do this analysis at your own pace as well. I'll just upload all of this to GitHub. So essentially, you just have to do this Docker launch. So this particular thing will, sorry, not this one, nim Docker launch. So this will essentially launch the Docker container image specified in this common env.sh. So you can change this to 3.170b and so on. So I'll just take you through this particular. Like, how can you do that? Yeah. So this is the NGC container website, similar to Docker. This is NVIDIA container catalog for Dockers, which are given by NVIDIA, provided by NVIDIA. So if you search for, let's say, Llama, you will get several models here, like SQL Coder, Llama 3.1405. So I took this particular model. Once you take this model, if you go to the tag, you'll see that this will give you, once you copy this will exactly give you the same URL or same endpoint that I just pasted in the common env I showed it to you, right? And this is, again, as I mentioned, this is pre-optimized container. This has several profiles. Depending on the underlying hardware, it will download the relevant profile, and we can also specify which profile in terms of quantization, tensor parallelism, or pipeline parallelism do you want to run this with. So there is an additional argument for profile in the GitHub repo that I showed to you in that VS Code repo, which you can specify and test with different profiles, which gives you the best performance. Right? So now we'll go back to the presentation. If anyone has questions, I'll just stop. Use a few minutes for questions. Yeah. So now we have seen like inference metrics, how does inference takes place and how do we benchmark them. Now we are going to deep dive into inference engine and start looking at the TensorRT to begin with. So TensorRT is, again, it's a open source library for optimizing LLM inference, particularly, and it provides optimizations including like attention kernels, these custom attention kernels, in-flight batching. We are going to see like how does in-flight batching helps us to reduce the bubbles in the GPU for batching, for particularly from the batching perspective, quantization like FP8, FP4, and activation-aware quantization, int8. So you can create different profiles or different variants of the model and then do the benchmarking. So you can build the whole pipeline and see which gives you the best inference performance. So not in terms of the user evaluation or model evaluation performance, but from the inference perspective, this you can build the whole pipeline using TensorRT LLM and GenAI Perf benchmark tool that we recently saw. So and this is, again, all built on PyTorch. It provides you a high-level Python API, which supports different inference setups like single GPU, multi-GPU, or multi-node, and so on. And it also includes built-in support for parallelization. So you can do different tensor parallelism or pipeline parallelism particularly from the inference perspective. And yeah, it's PyTorch native, so you can easily experiment with runtime or extend any functionality to include your own. So TensorRT LLM is built on TensorRT engine, which is particularly for the AI workloads, non-LLM kind of workloads, like your machine learning or deep learning models. You can use TensorRT and optimize those models by doing memory optimizations. We do optimized matrix multiplication of pointwise kernels and so on. So the TensorRT supports both multi-node and multi-GPU parallelism with model TP and PyTP. And there are other libraries like vLLM and SGLang, which also supports this multi-GPU and multi-node functionality. Now let's come to the inference optimizations. We saw like what are the different optimizations we can libraries, but now we are going to see like optimizations, particularly on top of these libraries like in-flight batching, KV cache, and attention techniques, and so on. So KV cache is very important from the inference perspective, because you do not want your attention modules to recompute the key and value cache, which is a compute bound process, to do again and again for the each generated token. So this KV cache attention techniques have like sliding window attention and streaming LLM, which allows, which basically sliding window attention is a technique which removes tokens based on arrival. So it's a first in first out kind of technique where the initial tokens were removed from the attention window to reduce memory usage. And although it can negatively impact accuracy or require recomputing KV after some point of time, if your accuracy is going down, it may require you to recompute as well. And streaming LLM, it does not have this removal of attention elements. It only removes like very important element, which is necessary for which has the higher weightage for the complete generation task, for the overall generation task, and it does not require recompute and impact accuracy. So both of these features are available within the TensorRT library itself. Now from in-flight batching, which is a runtime optimization. So again, this KV cache and attention is also a runtime optimization. That means when you're going to deploy your LLM, you're going to specify like do you need to adopt both these techniques or not. So in-flight batching is, but in-flight batching is one of the most important runtime inference optimization. It's batching strategy that differs from previous generation of previous models like CNNs and so on, because in-flight batching utilizes the fact that language models are autoregressive. So these models generate token by token, and to generate the next token, you have to process the model from beginning to end, right? So if you are going to generate the first token, you have to process the complete input prompt, and if you're going to generate the second token, you have to process the complete input, which we are storing in KV cache, and then the first token as well. So in-flight batching, each of these columns here is generating one token for 4 requests concurrently, right? So here for these 4 requests, one token is being generated. So in previous generation of the models, if you have experimented them, you have to batch. In order to create a batch of input request, you have to pad the request in the batch to the same length, right? Until and you have to wait until the last request has ended generation. And once the last request has ended, you can now supply the new batch. But in-flight batching differs in the sense that you can keep the request generating, because the new run of the same neural network while another one is ended, and you can add the new one here. So right, let's say request 1 is ended here. Now you can add newer request to the same batch once this R1 has finished. You don't have to wait for the slowest request to finish to append the new set of requests. So this has completely changed the inference performance of the overall model, and essentially it improves throughput, time to first token, and of course GPU utilization. And this is integrated directly within the TensorRT LLM Triton backend, which is an inference server. And and so this has made due to the autoregressive nature of the language model, this batching, in-flight batching has made it so efficient, unlike like CNN kind of models where we have to wait for the complete batch slowest request to finish before adding new request. And another important technique, which is not a runtime optimization, which is sparsity. And there are like different kind of sparsity, structured sparsity and unstructured sparsity. And particularly in structured sparsity, where every 2 elements of 4 can be zeros, and that can be stored in a more compact way, and you can benefit from the reduced memory bandwidth. So like your whole parameter matrix is reduced to half of the size than the original matrix, and this essentially results in lesser computation, lesser number of computation, and increased computation speed, and lesser memory bandwidth requirement as well. So it's not a runtime technique, so you have to train your model in such a way that it is sparse, and this requires you to do some optimizations like there are several sparsity techniques like sparse GPT, Awanda, like structured sparsing techniques, which helps you in reducing the overall parameters in the model without affecting the accuracy. And this is an interesting technique. It's both the offline, that is compile time, and runtime. And there are several methods that have been proposed for speculative decoding. But we saw initially that decoding phases are memory bound, unlike prefill phases, which are compute bound. And there are a lot of memory operations because you have to generate only one token and your attention is already computed and stored in cache. So here you can get benefit from additional computation. If you give additional computational tasks to the GPU in this decoding stage, you can take the benefit of the GPU computation, like reduce the memory bound overhead. So this particular decoding allows the inference system to generate multiple tokens during each step. So what happens is during each, so let's say I have this is particularly a Medusa algorithm. There are several algorithms for speculative decoding like read, rafter, eagle, and so on. But in this case, what is happening is it allows you to generate several tokens during the same time. So this particular head generate like token tweet, like let's say if you are generating token 1, then it will generate token 2, and the another head will generate token 3 and token 4 and so on. And then there is you can use, instead of using this, let's say this is a bigger model and you're applying this speculative decoding on the bigger model. Now you can use just a smaller model, a separate smaller model, to validate, to generate these tokens, and then you can validate from the original large model. Right. So I'll just repeat it. So what is happening is there is a concept of a draft model and a small model within the Medusa kind of speculative decoding. So in the while generating inference from the original larger model, you also take help of a smaller model which generate multiple tokens or at higher speed than the original model. And then you just have to validate the tokens generated by the smaller model with the original larger model. And this helps you in skipping few, let's say if your few tokens are validated correctly and deemed to be correct by the larger model, then you can just skip the generation of subsequent tokens by the larger model, and this helps you in saving the token generation time basically. And there is one modification of this speculative decoding, which is by Medusa, which is having multiple heads instead of only single head. So these are retrained. So your original model is retrained to learn these heads. So these heads are basically similar to LM heads, which is generation of for the original language model head. They have additional copy of these heads, and these heads learn the generation of the forward tokens or the future tokens. And then once these future tokens are generated, the LM head will progress with the original in the original way, like it will generate token 2, token 3, but it will just validate whether the tokens generated by these heads are correct or not. If these heads are generated tokens are correct, then it just skip the generation of the next few tokens. So there are like several literature, several papers which are doing this speculative decoding. But yeah, this is again very interesting, and people are trying several ways because now the models are getting bigger and bigger, and the tokens are also produced. Intermediate tokens are very large because there are reasoning models which generate large number of tokens. So now we have covered the inference model optimizations as well. Now we'll go to the serving part, because once you are completed with the model optimization, now you want to serve the model to the user. So you need to build a server and generate an endpoint. So how to bring your model to production and serve your model at scale. So there are various serving frameworks, vLLM very popular, SGL and Dynamo. So this Dynamo earlier was Triton. So now Dynamo includes this Triton inference server. And all of these vLLM, like if you have used vLLM, this is a typical, very simple setup of vLLM, like offline setup, where you just specify a model name and you do LLM.generate, and you will be able to generate the tokens for this particular given prompts. And LLM does support multi-node inference as well. If the model is not fitting on single node, like larger models like DeepSeek, 671 billion parameters. And similarly, SGL also have a multi-node inference support or disaggregated serving. But we are going to look more deeper onto the NVIDIA offerings like Dynamo and the Triton. So Dynamo is particularly for the disaggregated and distributed inference serving, which is on multiple nodes from the prefill and decode stage. And Triton is typically for the standardized model development, standardized model deployment. Yeah. So Triton is again, Dynamo Triton is an open source software for inference serving. It addresses the complexity of serving multiple frameworks, query types. So model can have different query types like real-time streaming or in batch mode. So it allows, in addition to that, it also allows audio and video streaming inputs where models can be, it supports like audio and video streaming inputs, and it supports several platforms like x86, ARM, Linux, Windows, and so on. And it can be deployed on public cloud, data center, or edge embedded devices, or even devices like Gypsum. And in addition to this, because once you deploy or create a server, you also need to do a model analysis, like whether your model is optimized for high GPU or high throughput or low latency. So it uses Prometheus and Grafana to send metrics, and it delivers all these features out of the box. So it does not, like, it shows very high performance on both CPUs and GPUs through features like dynamic batching, and model analyzer helps you in look for an optimal configuration for deployment. So like there are several features within this Dynamo Triton library SDK, which helps you in doing the inference serving. Yeah, so we somehow touched upon the disaggregated serving, but also do a mention about another feature, which is KV cache aware routing. So instead of assigning the request to the least loaded worker, the router will check which worker has seen the most similar request previously. So if, in other words, like if your KV cache is matching to the most to the input tokens, this KV cache can be reused instead of recomputing again for the another request. So this helps you in doing this inference faster and this cache aware routing. So this feature is included within the Dynamo Triton. So like this is again during the inference serving, it helps you in doing that. Yeah. And this is again disaggregated inference, which has like separate prefill and decode stage. So I will not touch much upon this because we have mentioned like what is the prefill and decode stage and so on. Yeah. And now this is the last slide that I just want to present in terms of like there are different use cases and which has like different demands for the input and output tokens, which eventually affects your inference serving. So if you can recall, like during the benchmark, we set this use case of input and output sequence length, which helps us in defining the what is the latency that we are going to receive under certain use cases, under certain concurrency conditions, and so on. So yeah, I just want to highlight this particularly, like for summarization, for reasoning, you have like short to long to extremely long context size is required. Yeah, I think this is it from my side. I'll just stop for questions. Yeah, we are on time as well.
Okay, then we'll wrap the session. Thank you everyone for joining. Thank you, Ayush.
Questions.
Session is concluded.